Okay, good afternoon. In today's session, I'll be discussing the analysis of continuous beam with variable flexural rigidity and with overhanging on one side or both sides. We'll see one such problem and how to analyze that by applying theorem of three moments. Okay, consider the problem. A beam ABCD 9 meters long. A beam ABCD 9 meters long is simply supported at A, B and C. Is simply supported at A, B and C such that the length of AB is 3 meters, length of BC is 4.5 meters and that of CD is 1.5 meters. And there is a UDL of 1.5 kilonewton per meter on AB and a point load of 1 kilonewtons at D. Okay, the moments of inertia of spans AB and CD are I and that of BC is 2I. Okay, double that of AB and C. So draw the bending moment and shear force diagrams for the beam. Okay, so the procedure is very much similar. There is no difference. Only thing, we consider the moments of inertia, respective moments of inertia. General expression will consider. Okay. What we have considered for uniform section is different slightly because we need to include the I value in that equation. Okay, for different sections. Also, the moment at C, bending moment at C. If you consider the right hand side, the moment that is produced by this is 1.5 kilonewton meter, isn't it? And at A, moment is 0. So these are true. That means the bending moment at C is 1.5 kilonewton per meter and bending moment at A is 0 irrespective of the load on AB and BC. Irrespective of the load on AB and BC. Unless the load on CD changes, MC remains same, 1.5 kilonewton meters. Understand? That means if you increase this to 15 kilonewtons, then also the bending moment at C will be 1.5 kilonewton meters. Okay? Is this clear? So, also bending moment at A, being simply supported, it is 0, irrespective of the loading on AB and BC. It is clear. Okay? Yeah. Keep this in mind. Now, let us apply the theorem of three moments for spans AB and BC. Okay? Now, we replace this overhanging portion. We remove that and we include this moment MC, which is 1.5 kilonewton meters. That means 1 into 1.5 meters. Okay. So, first the length of AB L1 we are representing it as L1 and length of BC as L2. Okay. And that of CD is L3. UDLW 1.5 kilonewton meter. Point load is 1 kilonewton. And moments of inertia of AB and CD are I and that of BC is 2I. That is all the data what is given. Okay. Now the bending moment in portion AB, the bending moment in portion AB due to applied load will be a parabola and with maximum ordinate at midpoint, which is WL1 square by 8. That comes out to be 1.69 kilonewton meter. Okay. Also, the moment at C is 1 into 1.5, that is negative. Okay, because it is hogging in nature. Bending moment at C is 1.5 kilonewton meters. As I told you, this remains constant unless the load on CD changes. Otherwise, it remains same. Okay, irrespective of the load on AB and BC. Irrespective of the load on AB and BC. Just like a simple support, where the bending moment remains same irrespective of the load, isn't it? Now, similarly, for span BC, there is no load, so bending moment diagram will be it is a 0 actually. There is no moment throughout the span. You will have 0 moment. Okay. Now, these are the final bending moment and shear force diagrams. So now A1 x1 bar, we will consider A1 x1 bar. That means for the bending moment diagram on AB, the area is A1 and x1 bar is from A, which is half of the span AB. And what is A1 for parabola? A1 is 2/3 of BH. B means span base and height is 1.69. Okay, 1.69. And how about x1 bar? Half of span. Half of span, 1.5. That means this x1 bar is 1.5. So this comes out to be 5.07. 5.07 A1 x1 bar. And how about A2 x2 bar? A2 x2 bar is 0. A2 x2 bar is 0 because there is no load. Okay, there is no load. So here the equation now, general equation for theorem of three moments is given by this. Actually, I1, I2, if they are equal, the equation will become MAL1 plus MB2 MB into L1 plus L2 and so on, isn't it? But here, being different cross sections, the spans being different cross sections, we include I1 term. The general equation actually we have derived this. Okay, L1 by I1 plus 2MB into L1 by I1 plus L2 by I2 plus MC into L2 by I2 equal to minus 6 A1 x1 bar by I1 L1 plus 6 A2 x2 bar by I2 L2. This is the equation, general equation. Okay, if I1 and I2 are equal, then it changes. Okay, now we substitute the values. MA is 0, so first term becomes 0. 2MB into L1 by I1, that means 3 by I. And here it is I, 2I, 4.5 by 2I, because I2 is 2I. Plus MC. MC actually it is minus. It is negative. Okay? Minus. This is minus, not plus. L2 by 2I. That is equal to minus 6 A1 x1 bar. We have calculated that by I into L1. I1 L1 that is I into 3. This is negative. And the second term is 0 because A to x2 bar is 0. The only unknown here we have is bending moment at B, moment at support B, intermediate support. Okay, that is only the unknown. So this becomes 10.5 MB by I, and this is minus 1.5 into 4.5, this is 0.75 by 2 equal to minus 10.14 by 3 I, 10.14 by I, because this 3 cancel, so it is negative 10.14. Okay, so I gets cancelled on both sides. So 10.5 MB minus 3.375 equal to minus 10.1. So MB is equal to now 0.65 minus 0.65 kilonewton meters. That's all. That is the final bending moment at B. Okay, and we can find now the shear forces. Okay, shear forces we can find. We see the bending moment diagram for this. Okay, we see the bending moment diagram. At A, bending moment is 0. At B, bending moment is 0.65 minus. Okay, that means when you consider this, it is considered for both BA and BC. Okay, this is minus 0.65. Okay, so this is fixed bending moment. And how about bending moment at C? Bending moment at C is minus 1.5. Minus 1.5. It is minus 1.5. Okay. Yeah. Here it is minus 1.5. 0.65 this, and this is 1.5, and 0 at D. And overlap this free bending moment diagram on this. Okay, that's all. This is all negative. So this is how we draw the bending moment diagram. Drawing fixed bending moment diagram plus free bending moment diagram overlapped on that. Superimposed on that. Okay. Yeah, that's how we proceed. And shear forces. To find shear force diagram, we need to first find the reactions. For that, we consider the free body diagrams of spans AB and BC separately, and we'll find out. Already we have discussed one such problem. We are not going to discuss that now. Okay. Yeah, considering free body diagrams, which are nothing but simply supported beams, AB, okay, and BC. There is no load on this BC, only end moments here. Okay. Yeah, we'll find out RA, RB1, RB2, and RC. The total reaction at B is sum of RB1 and RB2. That's all. Okay. Next, another example, let us consider a 3-span continuous beam with NDA fixed. Okay, NDA fixed and overhanging on support D. So, how many unknown moments we will have here? moment at A, moment at B, moment at C. So we have three unknowns. Moment at D is known, which is 3 into 1.5, 4.5. As I told you, this remains constant unless until this load changes. For any other load on spans A, B, B, C, and C, irrespective of the loads on the other spans, MD remains 4.5 minus. Okay, so NDA being fixed, we consider a zero span here. Okay, there is L1, L2, and L3. L0 is 0. Zero span will consider to the left of A, fixed end. So let us go through this. A, B, C, D, E has a built-in support at A and roller supports at B, C, and D. DE being an overhang. AB is 7 meters, BC 5 meters, CD is 4 meters, and DE is 1.5 meters. DE is 1.5 meters. So the value of moment of inertia is varying. Moments of inertia are not same. For AB it is 3i, for BC it is 2i, for CD and DE it is I. Okay. The beam carries a point load of 10 kilonewtons at 3 meters from a uniformly distributed load of 4.5 kilonewtons on BC, and a concentrated load of 9 kilonewtons in CD, 1.5 meters from C, and another point load of 3 kilonewtons at free end. So here on spans AB and BC, we have eccentric loads, point loads. Okay, and UDL on span BC. UDL on span BC. Okay. So same procedure is same here. Only thing is we consider zero span here. We have discussed already, I think, the continuous beam with fixed ends. Okay. So first three moments theorem is applied for spans OA and AB. OA and AB, which gives an equation in MA and MB. One equation will get. Next, apply this for AB and BC. This gives an equation in MA, MB, and MC. Second equation. And apply this for spans BC and CD. This gives another equation in MB and MC. Third equation. So we solve these three to find the moments MA, MB, and MC. Okay, that is the procedure. And before that, we will find the moments at F, moments at G, and midpoint of BC, so that we can draw the new diagrams on AB, BC, and CD. Okay. Okay. This is all the data what is given. Okay. So mu diagram on AB is this one. That means moment at F is W A B. A is 3, B is 4 by F. Okay. WAB by F. So this comes out to be 17.14 kilonewton. And here it is WL square by 8. W is 4.5 into 5 square by 8, which comes out to be 14.06. And on CD, bending moment at G is again WAB 1.5 into 2.5 by 4, which comes out to be 8.44. 8.4. Is this clear? So after drawing these diagrams, we will find out A1 X1 bar. A1 means this one. A0 is for span, 0 span, which is taken to the left of A. We are applying first for these two, isn't it? So these are the moments what we have calculated. A0 X0 bar is 0 on 0 span, okay, and A1 X1 bar is area. This area is split into two parts, okay, because it is not symmetric about its center, so it is split into two parts. For first part, it is the moment of this area, and for second part, this is the moment. Moment is taken from B actually, because we are applying for OA and AB. So the moment is taken from B. Okay, this is for part 1 and this is for part 2. So we are getting it 220. Okay, and when you apply the same for spans AB and BC, A1 X1 bar is calculated. This time X1 bar is calculated from A. X1 bar is calculated from A because we are applying for AB and BC. The distances are calculated from ends A and C. That means X2 bar is calculated from C, X1 bar is calculated from A. Okay, and that you need to be taken care. And similarly A to X2 bar. This time the moment over this, okay, which is 117.2. And for spans BC and CD, this A to X2 bar, when you apply for BC and CD, this time we consider X2 bar from B. Here we are considering from C, but here we are considering from B. That you have to be, because it being symmetric, both are equal. Both are equal. Similarly, A3 X3 bar is 36.7. Now you substitute the values here. This term is 0. So first equation you will be getting this, and substituting these values. Okay, I1, I2 are different again. Substitute those values. You will get the second equation here, and substituting the other third equation we will get here, and solving. So procedure is same. That's why I'm not explaining this in detail. Okay. So solving these simultaneous equations, we will get the moments MA, MB, and MC. And we will draw the bending moment diagram for this. That's all for today's session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.